Dzień dobry. Hello. Good morning still. It feels like, since there's been so many talks, you still don't really feel like it's the morning since it's so action-packed, but here you are, it's still the morning, still quite a long day to go. And my talk, how loaders continued Outwit AI, EDR, and sandboxes. And what's quite funny is that I actually feel that the talk's going to be almost quite related to like the two talks that were previous. And they came from like a very red team side. And so I'm actually coming from more like the blue team side, the people that are the victims of the previous speakers. So we are, and so basically, go and talk a little bit about loaders and honestly share a few stories about how frustrating that makes our lives. A little bit about me. I'm Ryan. I'll not say too much. The photo, I was in Gdansk in 2018 whenever Poland were playing in the World Cup. It was a great day for me, but honestly, not a great performance from the Polish football team. So I'll not talk too much about the World Cup. I'm a security researcher with Intezer. Basically, my main role is sort of reverse engineering and maintaining a sandbox, sort of malware analysis tools. I've been like a reverse engineer malware analyst for about 8 years now. I'm maintaining a sandbox for around 4 of those years. I've also in previous roles worked as a security engineer, so sort of working on both sides of like the vendor and the consumer of security products. A quick agenda that we're just going to blast through is that I'll give a couple of sort of kind of definitions of what loaders are, but we'll not spend too much time on it. I'll give some examples just to jog your mind. You'll probably know a lot of them if you work around this field. And then the main core of the talk is that I was saying, like, how would one begin to unpack it, or what tools are available to a blue team, that's able to deal with what's being thrown at us. And then I'll kind of talk and compare it to like an arms race, because you'll see that there's just this constant cycle of escalation. And one of the stories I'm going to share is that I think it's getting to pretty like ridiculous kind of levels of what sort of loaders and crypters are doing to get around the blue teams, and again, people maintaining sandboxes or EDRs. And then you can't really have a talk in 2025 without talking about AI, so I've managed to put a little bit of that in. So to give sort of one-liner, quick kind of definitions, to say a loader, it is to execute a payload on a target system. Cryptor, obfuscate and encrypt malware code. And packer, something that's used to compress or obfuscate binaries. Personally, they're often used interchangeably, or like people don't use exactly like hard lines about what's a loader, what's a cryptor, and all, because honestly, what you see these days, it kind of incorporates all 3 of these concepts. So yeah, it's often used interchangeably. I don't really care what you call it, because again, people are going to use different words for it, and the main thing for me is that you are trying to hide something from me, and it is my job to make sure that our product can deal with it, unpack it, detect it, run it, whatever you want to do. So, some examples. Things like BruteLoader. It's actually been like really successful, been around for a while, and very actively maintained, and it just constant innovations with BruteLoader. One of the more recent ones is it uses vectored exception handlers. So it does, to obfuscate like the control flow and get around in some sandboxes. Whenever there's an exception that happens, it sort of decides that it breaks and stops. So it's really effective at getting around like sandboxes, EDRs. Smoke loader, again, a very famous one, been around for a while. Coffee loader is one I saw quite recently that I quite like. Really full of like anti-sandbox and anti-analysis techniques, so a bit of a pain to deal with. There is IDAT loader. Personally, I come across this quite a lot. During my time as sort of reverse engineering. And the reason why it's called IDAT loader is that that's a string within a PNG image. So it uses a bit of steganography, or it'll drop a PNG file in the temp and then extract the payload out of that to put in the memory. There is the donut framework. And so technically, don't know what the open source project is called, like the shell code, but you're able to generate multiple loaders for that to run Donut, and we'll actually see it come up in the talk again later. And gzip loader, I put that one in because I quite like it. It's quite fun to deal with. I think it's quite easy to detect that one, and it's used to deploy IcedID. And again, I've come across that a few times. But basically, there are many, 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 many examples of loaders. New ones each day. You see like new Crypters, new everything, because there's quite like a big market for these, Constantly what you have, especially in terms of like stealers, sort of like Trojans, is that, those in themselves are quite easy to detect. So where most of the innovation comes from is the loader side. Like, how do we deploy this malware that in itself is easily detected, but how is it deployed in a stealthy way? Because that's more sort of what matters. So how to unpack, and I don't exactly want to go through like a technical way of saying like, no, I'm doing this, no, do that. I'm just sort of going to go through a few stories and basically tell you what technologies that we have at hand to unpack it. And again, personally, what I'm working with. So one is a static unpacker, and basically what it is, it's just a script or a program, a piece of code that basically when you identify what the loader is, you know what the unpacking mechanism is, basically the script or code, it's able to mimic what that unpacking mechanism is and basically just get the payload straight out. And you can do this without actually having to run like, the malware or like the loader to file or anything. It's a very quick, very clean way of getting a payload. The main downsides with it is that if you have a loader as constant innovations or is changing things up, changing encryption mechanisms, you're going to have to keep updating your code base in order to deal with that. So again, quick, clean, cheap, but not very flexible in terms of anything's being updated or actively maintained. Another one is an emulator. Personally, we don't use this too much in regards to the way I work, or at least in like a production environment. But in terms of like research, if anyone here really does any kind of malware analysis, it's kind of one of the tools that you have in your toolbox. I use Queeling quite a lot, built off the Unicorn engine. But basically what an emulator is that it simulates a computer, simulates a CPU. And what it's really good for is that if you have a relatively simple unpacking mechanism, that might have an encrypted payload, it's able just to go through those decoding instructions or decryption instructions, and then you're able to hook whenever, at like a certain point that you define, usually on a call like, say like a VDLL or VRTL, you will hook in that call, and then you'll just take whatever, whatever kind of memory region that that's pointing to. And again, you will be able to get the payload from that. One thing is that you do kind of have to maintain like a file system for it. So if there are certain sort of DLLs that are being used, you will have to get that. So say if you go for something like Queeling, you will have like scripts that you're able to actually run on like, say, a Windows computer that you have, or like a virtual machine, and get the kind of file system and all the DLLs to work with that. And the most flexible one, and the one that personally I work with the most, is a sandbox. And I am probably going to hazard a guess that most people within this room have used some sort of sandbox, or like Joe Sandbox or AnyRun, maybe even Intezer's one. And it's basically the most foolproof way of unpacking a loader or running a loader. But it's also like the most expensive way, because you have to have your snapshots and maintain, basically maintain like a virtual machine, and that you'll actually run on some hardware, be it actual hardware you have like servers, or maybe up on like a cloud server. We see a lot more these days. So most foolproof, but also like most expensive. So I'm going to go into some stories. Again, I don't exactly want to give you like technical this and that. I've kind of been doing this for a few years, so there's some fun stories. I'd actually quite a few stories in, but I needed to like take a few out in regards to time, because I sort of practiced this talk beforehand, and I thought like maybe I'm running a bit over, or there's kind of one story in particular of the most recent examples that I've come across that I want to get into. So what I'm going to do is basically talk about an example of a static extractor, and then talk about sandboxes after that. I don't want to get into emulators too much since I'm not using it in like a production environment, and it's kind of a nice comparison between the two. So a couple of years back, BruteRetell, it's a C2 framework, kind of similar to what Dom was talking about at the start. Kind of like Cobalt Strike and the Nighthawk tool that they provide. That you have a GUI where you're able to set up a listener, a C2, and then generate a payload, and then this payload is delivered through some mechanism. Then you're able to perform red team operations on whatever sort of target machine that you're going for. So mainly kind of red team. Basically, what happened is that a version got leaked a couple of years ago, and then cracked by some group and leaked online, and then suddenly it sort of around then started spreading quite a lot. We saw quite a few examples of it. I don't see as much now. Again, there was only one certain version that got leaked back then, and that's sort of a picture of what it looked like, the crack. And again, for anyone that's used like Cobalt Strike or something, you'll maybe realize that it's kind of similar to other kind of C2 frameworks. So, but when you generate a Badger payload, Badger is a bit like the Cobalt Strike beacon. The first thing you come across is the BruteLoader. So there's a loading mechanism before you actually even get into like the C2 framework being executed itself. It's very easy to actually identify this, or at least for this particular version it was, because you kind of see all these push to these registers at the start, and then suddenly all these stack strings being moved over. And it kind of comes in two main blocks, is what I call it. Is that the first block was a configuration, and it's like a base 64 string that when you decode it, you find out it's also encrypted. And when you reverse engineer, you sort of find out what the encryption is. And then there's a second block that it's just full encrypted data, and that is the Badger payload. So basically, the main thing is that whenever we try to protect our customers, again, if this is being leaked and used, we want some way of being able to make sure to unpack this, that it works in our sandbox. We have to maintain stuff quite a lot, but in this case, it was a very good example for a static unpacker because it was just one version that was leaked, and so it was building like the same sort of payloads each time. And since it kind of stayed the same, it was like very easy to write a script for. So again, you go through whatever your tools are, like IDA or in this case x86 debugger, and you find out that it builds up the two blocks, and you get. In this case, the first block, you look, and it's a base 64 string that is a configuration. You see that the second block, it grabs the bytes right at the end, and it uses an RC4 mechanism to decrypt that. And already there, you have the Badger payload. But what is quite interesting in this is that, yes, a lot of times that you can get the payload and you can find that out. You don't necessarily want to stop there, especially when it comes to these C2 frameworks. What's very nice is to do like a configuration parser. And so, again, you basically keep reverse engineering the loading mechanism. And with that, when what happens is the RC4 decryption happens on the Badger payload. You get the decrypted Badger payload, and then there's a second RC4 key, and then you're able to use the second RC4 key, able to get the configuration out for that. And now you see that it's very clearly a configuration. You see, all the fields that are there, but you don't necessarily know what those fields correspond to, since you just see the data there. And so, what was very nice is that since the builder was actually leaked, you're actually able to reverse engineer the builder for this. And when we reverse engineer the builder, you're actually able to find out what the structure of that configuration looks like. And in this case, you see that the previous one was like the HTTP or DNS over HTTP payload. Again, kind of similar to what Dom was saying later. You see stuff like the jitter and what like the URL paths that are being used. But you actually see there's also TCP and SMB modes that have like very much smaller configurations. So even from that, you're able to find out fully exactly what that looks like. So for us, it comes to the time, OK, right, I actually have to make a script and a static extractor for this. So what I do first, and I'll just sort of go through the script kind of quickly, is that you can define in a byte array, what those push, like the registers for the pushes are, and you can use to then locate that in heavy memory. Because again, you can like generate sort of shellcode for this BruteLoader, so it can kind of be embedded in kind of multiple different things. So basically, for me, the best way to identify how to find the start of the loader was to just look for all the push arrays, and it was very, very successful. And then one tool that we use quite a lot is Capstone. Again, people maybe use stuff like IDA or sort of Gija for disassembler, but in regards to doing something, in like Python especially, or kind of building code behind it, something that you want that's reliable in the script, I use like Capstone quite a lot, and we would even use it within production environments. Like it's really, really good. If anyone wants to take a look at it. So basically, we start to use Capstone, and literally, we've reverse engineered, so we actually know what like the loader looks like whenever you're going through that. So basically, what I've done was, you go through and you find all those stack strings that are building up the 2 blocks within the stacks, and now you have to do some padding in regards to getting what it's like cracked that block. If you don't kind of sort out your padding, it'll kind of throw like the blocks off. But you basically go through, you find your 2 blocks, and then you go through like the decoding mechanism again that you find out from reverse engineering. So in this case, it's that you grab the second block, decode it, you get the Badger payload, the second RC4 key, and then do your base64 decode, and then your second RC4 decryption, and lovely, you get your configuration that. And so that's kind of what it looks like whenever you see like the DLL for like the Badger payload. So already with static extractor, you're able to reliably get that payload. Again, it doesn't change that much, but since you can go one step extra with C2 framework, you can also take what you've figured out from reverse engineering the builder, and you can then just put, say, something like a pretty printer. So it'll kind of look like that in the end, and that's sort of, again, one of our tools that you can use to defeat like a loader like that and get very reliable information, and then actually IOCs to pivot off. But like I said, it's not the most reliable. So it's not, again, if anything changes, and I have seen further versions that have come out from actual like not like threat actors, but like the red teaming ones, and it's been changed. So again, does it only work for one like particular version, and then everything changes? So that's why I want to get on to Sandboxes, and I've got 2 main stories for it. Yeah, I guess we'll get stuck into the first story. So again, a couple of years back, I was pinged by a coworker that basically said, hey, look, a customer tried to run this file, and it didn't do anything. Like our sandbox run for it was kind of naff. It runs and stops, and we don't really know why. But the customer's POC in the product, so kind of come to me and go like, we have to make this look good. Basically find out what is happening, so we can actually improve the product. Again, it's always making sure that you can improve the product, and making sure that you get reliable unpacking. So for this, first of all, you see there's a very large amount of junk code. So as a reverse engineer, it's kind of like, oh, okay, right, cool. And basically, when I managed to get through all the rubbish, I found out that there were a number of checks. And so the traps that it had, and actually for a script, there's actually quite a lot of anti-sandboxing checks. So I found this quite interesting. But first, there was a CPU core count, and it basically terminates if the system is less than three kind of CPU cores. It uses Windows management instrumentation to do this. So actually, kind of similar is brought up in the last talk. And basically what it does this is that if the computer seems like kind of weak or like kind of small, it kind of makes the determination, right, this is maybe a sandbox and jumps out. And the reason for that is like I said, in order for us to run these sandboxes, they cost money each time they run. To spin up your VM, you've got to like host it, especially if you've got like a isolated server for it. So we want to find that kind of balance of having like small amount of costs, but reliably unpack. So we'll go through a couple more. There was a process blacklist. So basically a large kind of blacklist of process names, and it finds if any of these processes are running, it will terminate because it's being analyzed. So stuff like kind of Fiddler or IDA or kind of debuggers, like many things. It done a running processes count. This one's pretty common, but you'll see later that there are kind of different ways of doing this. And it basically exits if there's fewer than 28 processes currently running. Again, we're trying to run a lightweight sandbox, and but that you see you need to have like a certain level of kind of noise. These days, in regards to Windows 10, Windows 11, that's just opening like an Edge browser. I think you'll get about 200 processes. It would check if there were fewer than 3 files in the temp directory. Again, that's not normal for, it's to have less than 3 files. That is not normal unless you've just done like a recent clean out of your temp folder. It would also do the same for the downloads folder. Again, people download quite a lot of things, so if you're not like good at cleaning up your computer, that's not normal. It would do a disk size check for if any disk is smaller than 50 gigs. It would check the system uptime. This one I actually don't see too much, but in this one it did. So it basically terminated the system being up for less than 10 minutes. Again, like your grandmother's probably not going to speed run like like a malware infection. So again, that's another indicator. It would do a RAM size check. That one's pretty small. It would do a file presence check. It would drop this file as like a way of indicating almost kind of like a mutex. So that check is more or less of an anti-sandbox check and more of like a, hey, have I already ran? And another one was a loop skipping check. So it basically build up a loop and sort of append to this kind of variable. And what it does is that it's kind of like the tick count one, if anyone's seen where, for sandboxes, again, we're trying to get the result to the customer like very, very quickly. So we'll actually implement stuff, and I had a lot of slides that I took about how we actually do a monitoring DLL to hook API calls that are going to like Win32 and stuff. And so when we hook these calls, often if we get like a large sleep, because again, lots of malwares are sleep for say like 5 minutes and all. Well, if you're doing a sandbox run, you don't want the customer sitting there waiting, tapping their watches. We just kind of skip them. So it basically checks if we're trying to like skip any of these long calls. Again, in this case, it didn't do a sleep. It just built up a really huge kind of variable within a loop. And so basically what I had to do is that, I know it's not working in our sandbox. So what I had to do, and I had a bit of time, I actually just got the vaccine at the time, so I was busy up at like 2 a.m. So I was like, I'll write a script that we can drop into our sandbox to figure out which of these checks are actually failing. So again, just a simple Python script that essentially just mimics what the Visual Basic script was doing. And then I contacted one of our engineers, and so she was able to basically go onto the KVM and spin up a from our sandbox image, spin it up and run the script. And so we basically found that we failed the CPU check, we failed the band process check, we failed the disk check, and we failed the uptime check. And to basically put this in perspective, it was actually in the early days of like when we started to maintain our own kind of sandbox. And so a lot of these things were kind of new to us at the time, that there's lots of things that aren't out. It's a bit like, again, if anyone has like a virtual machine, you've got all your snapshots of when you're trying to build up your analysis environment. And it's essentially the exact same for a sandbox, is that, you have these malwares that you find out have these anti-sandboxing techniques. So you basically go on to onto that sandbox and start to add like noise. Start to add junk within the temp folder, start to add junk within the downloads folder. In this case, run it for over 10 minutes, and then take your snapshot. Then, so I had to go over to engineering, and they implemented the fixes, and boom, we were able to unpack it, and it was Ersniff. But the main kind of story behind this is that whilst a lot of these checks are like very simple, there's just like a constant like cycle of having to find malwares to be able to avoid your sandbox, and then go implement those changes, take multiple snapshots, of those fixes, and then deploy that back up the machine, and that's a constant process. And we actually have to like keep doing this and make sure that you have like a good, kind of like change log of activities, because whenever we were first doing this is for a Windows 7 machine, and then Windows 10's come out, and eventually we're going to have to do this for a Windows 11 machine. So even though some of these checks are kind of old, you actually have to keep doing it. So you do. And so I want to get on to my next story. And I call it like blah 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 blah. And so to put context, this is like a really frustrating story for me, and this is one of the more recent loaders that I come across, and is really quite sort of diabolical. And how it came is kind of similar to the last one, where I get contacted by one of the customer service people saying, "Hey, we have a customer POCing our product, and actually, they've taken a look at this file that one of their employees has had and ran. Our sandbox is not getting a good result." So again, there's kind of two things. We've got very good customer support in this. So first thing is reply to the customer in a very quick time, because they want to find out what the payload is. Because if you think about it, if you look at the payload and then you find it's like a crypto miner, it's kind of just a cleanup. But if you run the payload and you find it's like a stealer, well, then that's a much bigger problem for them. And depending on what sort of data they have, if they have like customer data or stuff like that on their computer, like never mind the incident response team, they might have to like call a lawyer. So it's very important to reply to the customer quickly and then improve the product. And so the first thing I notice when I open it up in IDA is it is big, really, really big, and I genuinely really struggled to convey how big this was in terms of like assembly instructions and code in one function and like the main method, utterly diabolical. And I've tried doing ways where so big that I can't even take like a screenshot to show like the graph, because I was even thinking about going to like a printing company before coming here and printing out a bit of paper to show the assembly instructions how big this is, but it would have cost me too much money. On Twitter, I've done like a video showing scrolling through the code, but I have another way to describe how big it is. So a frame of reference is that this is Tolstoy's War and Peace. I actually believe it's multiple books, but in one book it is really, really big, and for a reader from like 200 words per minute, it'll probably take you about 4 months to get through. And so it totals, I think, just under about 4 million characters. One method, the main method in this loader, was about 3 times the size of Tolstoy's War and Peace. And I had 24 hours to reply to a customer. So okay, right, cool. So now, obviously, those who reverse engineer know that you don't necessarily need to go through every single assembly instruction. Like over the years, you kind of build up this like pattern recognition. You go, well, actually, it looks like I want to go there. Maybe I see like this call or that. But the problem is, this was just filled with so much freaking junk code. Like junk code's common before. You saw it within the VBS script beforehand. Just code that is put in that doesn't actually do anything, but it's there just to waste your time, to like bog you down. Like, I don't know why too many people haven't done this before, but basically you do junk code and you just dial it up to 11. So I'll basically show you what some of that junk code kind of looked like. Oh yes, and sorry, I want to say my tools are collapsing around me, and IDA nodes is feeling too big to display. My Engager, the decompilers, like, no, you're on your own. even in binary ninja, it's like this function's too big, go away. You can't actually force analysis, but at the start it goes like, yeah, no, that sounds like a you problem. So anyway, what does it look like? Basically, there's just so many of these calls where they kind of look like they're meant to be important. You know, if you're reverse engineering, if you see stuff, you know, like a copy file or like a decrypt file, you know, writes and reads, you go, oh, maybe, like maybe that's important. And I mean, like again, I've got like 2 of these ones up, and like, you know, you see all the strings, but it was just thousands upon thousands upon thousands of them, and you have to actually try to figure out what, you know, this thing is doing, how it's getting around our sandbox, just in amongst, you know, people talk about a needle in a haystack, but this is just dialed up to the umpteenth degree. Another thing is that there was just all these operations, just moves and ands and operations. I mean, just thousands upon thousands upon thousands of them. And there are actually like instructions that are relevant, but it's kind of buried in. So you get a relevant instruction separated by thousands of instructions, and then the next, you know, the next one in line has thousands later. So it's really, really annoying to deal with. So just, I mean, walls upon walls of this, and again, I can't even put in screenshots to describe to you what this kind of looks like. Another thing is the control flow, and what I've actually done to compare here is these are actually 2 different samples of the same loader. But you see that the control flow is actually very different in each. And basically, I think people heard of polymorphic malware, but this is technically what's called a metamorphic malware. So this loader, for every single build of the loader, you know, obviously it changes the junk code that's in it, it changes the control flow, it changes the strings, it changes the calls, it changes the encryption, it just changes everything. And so, you know, this makes it really hard, like for your defenses, if you want to make like a Yara signature or stuff like that, just everything changes per build. You know, for our company, we do like genetic code analysis. So, you know, we'll sort of see assembly instructions that we're able to break down in the genes, but it just rips that all apart. So it does. And even the metadata inside it, you know, just, you know, so sometimes you can make like a Yara signature or, you know, stuff that is off like the metadata inside the code, but again, everything just randomized, completely random, that you just almost can't like get a grasp on. It's so slippery. You know, it's kind of funny. Again, for this stuff, you're able to tell that it's malicious, but you know, for a lot of people, that is enough. Where like it goes, yep, I see it's trying to obfuscate something for me, therefore it's bad. But for us, our main thing is to actually find out what the payload is, and again, unpack it. So we have to find out what it's actually doing. More defense mechanisms, and actually this one's quite normal. You'll see that there's API hashing and dynamic API resolution. So luckily there was actually a couple of functions that were reused in regards to this. So you know, I was able to put breakpoints inside them and sort of get an idea of how it's trying to like launder the shellcode. So in this case, what I was using was NT-create section, and for this, it's a great way to get around emulators. So for emulators, since it's only simulating a computer, it's not able to do everything. And so especially if you have like functions that are doing inter-process communication, like basically calls like this, unless you hook them and then implement, you know, your own way of kind of handling it, it'll just kind of fail in an emulator. So basically, it would go through these calls, again, separated by mountains and mountains of junk code. It would create a mapped view. It would drop in the encrypted code. And how it would do it is that the encrypted code was, again, placed in multiple different chunks around multiple different parts of the binary. And so, again, every single build completely different, where it would sort of cobble it together from all these different far-flung regions. And then it would decrypt it. But it would also, the decryption mechanism also changes per build, and again, just, you know, to this day, I have actually no idea how, like, you know, if it's like a standardized like decoding mechanism or encryption, because there's just so much junk that I can't even tell. But eventually, you see when it is being decrypted. Another really interesting check is a graphics adapter check, and so what it does is that it uses DirectX DLL. And checks the graphics adapter, and it has a whitelist, so it basically checks for these, and it basically says, if you do have these, you're probably a real, like you're a real computer, like a real laptop or something, because you know these are very popular kind of vendors. Again, when you first spin up your sandbox, you kind of don't you kind of don't think about stuff like this, where you're like, that your graphics adapters or something kind of virtualized, or like a VirtualBox one. And the funny thing is, right, this is not often used, but it's actually not new. And so one of the main points of this, I say how like loaders continue to outwit the vendors. Technically, a lot of these things aren't new. It's just that they're implemented in new ways, and that is genuinely enough to throw EDRs and again like sandboxes off. It's like there's a million ways to do the same thing. And so for this, what was like kind of new about it is that they would just do like a simple XOR calculation, which again, it's pretty simple, but it was just separated. A bit junk there, but it's separated by thousands and thousands of instructions. So you'll maybe find that, and then it'll take you like an hour to maybe find that, and then it'll take you another hour to find that. And eventually, once you see once you see that XOR, you'll be like, okay, that's a vendor ID that it is checking for. Another thing, which is I'm going to say this is slightly more new check, is that I call it a VDLL check. What it is that for Windows Defender, they have an emulator inside the antivirus engine, and so new files that come on, they actually run like a quick emulation of it, and and they're able to possibly unpack or find any kind of malicious characteristics. Again, like a bit of a lightweight sandbox that your EDR would do. But this actually came from they found out that this call in kernel 32 DLL, it actually doesn't exist in the real kernel 32 DLL. So this screenshot is from a talk that was in Black Hat a couple of years back, and it turns out within this VDLL that they use within the emulator, there are actually calls that are unique to that DLL. So what's kind of funny about this is that instead of trying to like fail it on something, if this call succeeded, the loader would be like, ha, I know I'm being emulated, and it would know when to bail out. So it's very smart. So any tools that you use, like I said, any analysis tools, or anything, it can just be turned back and used against you. So quite fun. Again, you think you're building your tools to get around. We study them, they study you. There was a unique process counter, so a bit like you see with in the Visual Basic script that was a couple of years back. There's nothing new about this, but the way that they implemented this, I have not seen before. So whilst in the Visual Basic script that it was using Windows management instrumentation, what this done, again using dynamic API resolution and all, it created a snapshot of like the systems of the running processes, and then it parses through that structure, and it basically created like a bit of a checksum on the name. So it took a checksum of one name and then compared to the checksum of the next name of like the running processes, and if the checksums didn't match, it would know that is like a unique process name, so it would increment a counter. In this case, it was looking for 85. So you see, a couple of years ago, it was looking for like 28. Now it's 85. Like I said, like I kind of said, you open like an Edge browser and you get about 200. So, and eventually, when you get through all that, there is a donut loader on the other side. And then it would drop a white stick stealer when you get through that. And whilst this is about the stealer and technically not about the loader itself, just sort of echoing what Dawn was talking about in the first talk about getting around kind of network, I just really wanted to highlight this because it was cool. It had what I would describe as like a Tor bind shell. So basically, Whitesnake would run, and it would reach out to this the repo here, Tor for Windows, and it would set up a hidden service. So it would literally connect to the Tor network, set up a hidden service, and generate an onion address for the infected computer. It would then do a dead drop of that onion address out. And since it's connected to the Tor network, the C2 is able to connect to the onion address of the infected machine and basically get in that way. So it's like a bind shell that's able to get around a firewall, which I found was kind of amazing. So yeah, anyone that's developing any C2 kind of frameworks, like try Tor. And again, since everything's encrypted, slightly a bit more hard to find out what's going on if you don't have like sort of things to break that encryption. Again, for Tor, it's probably quite hard. It's encrypted kind of multiple times. So again, only about 5 minutes left, but it's good I skipped a couple of stories. So, oh yes, actually, sorry, of course, you can't have a talk in 2025 without talking about AI. So this was last year that I looked at this loader, and I kind of made a Twitter thread about it, just complaining, you know. And one of the things I kind of said is that, you know, like, I haven't, like, run this against any, like, AI reverse engineering tools. To be honest, I don't really kind of use them. And again, I probably should try using them more. They're probably getting kind of good, kind of useful. But basically, my sort of theory back in the day was that, you know, look, this is really big, and you know, if you're thinking about like kind of tokenization, like you're really going to throw that all in, and like you know, how much money that costs, and since all these fake calls and things like, how is it even going to track anything? So my theory last year is that I think it'll be kind of cooked. So for the purpose of this talk, my coworker has Binary Ninja Sidekick. So we chucked in that and just kind of done a high-level test. And you know, so we just said like, hey, what is this single function doing? Again, one function. You sort of see it inside. That is just all code. So we basically said like, hey, what's this doing? And I'll focus just on a couple of things that it says here. But I was so happy it got stuck. Again, I was so happy because I was like, you got stuck in the junk code. Well done. You know, it says key strings and critical functionality. Again, people use kind of LLMs. You see how confident like ChatGPT is about stuff. It's like, yeah, totally. And this, so it's like, you know, these are key strings, critical functionality. This is all junk. None of these calls are actually like used or done. Like, but you know, something that kind of looks important. You go, oh, decrypt file. That sounds pretty important. The AI thinks it's important, and no. All complete rubbish. We asked it like, look, but what's this function actually doing? And it goes like, to be honest, I don't really know. And then it actually started to doubt itself. It goes like, actually, you know what? Maybe it's not malicious. So I found this quite good. So yeah, that's how AI. Again, I imagine if you use it in a bit more directed fashion, like, hey, I'm looking at this exact variable, this and that, you know, like using it, again, as your sidekick, as your debugging might be good, but from a high level, if you're using this kind of as a layman, it's a bit cooked at the moment. Again, will probably get better in the future, or if one can kind of harness it better. So basically say, like, this is an arms race, you know, like this, it's just a constant cycle, just year after year of like, you know, the security vendor puts something in, and then, you know, they'll put in more anti-sandboxing techniques, and then we'll put in like anti-sandboxing, and it just keeps going, and it's been a slog for years. And so like pain points that I have about it is that I said there's overwhelming technical complexity. You know. Like, I'm not the best reverse engineer in the world. I've been doing it for about 8 years, and so I think I've got to like a half decent level. But you know, for those who know, like it can, you know, when you're looking at like mounds of assembly and all, it can like it is like, especially an initial hurdle getting into reverse engineering. It can be quite hard. So, and not every company has access to these kind of resources. Now, not every company is maintaining their own sandbox, so it might not be their problem, but. Yeah, it's hard to get access to people that can actually kind of deal with this. And again, AI is not 100% helping at the moment. Cognitive and emotional toll is probably like half the reason why I'm on the stage, just because I wanted to complain. I was just, when I saw this, I was like, oh, like, seriously? Like, you know, when I made a tweet about it, some people are like, yeah, that's why I didn't get into reverse engineering. Like, you know, it took me just weeks to get through this, and it was just a slog. So it was like, and it does, like, it really burns you out, you know, for those, again, who program, who reverse engineer, like it can kind of hurt just staring at a screen, like, for hours, and, you know, after week, just trying to bust your way through something. So it's mentally fatiguing. So tool breakdown fragility, you saw that, like, my IDA was breaking, and, you know, just everything's collapsing around me, and AI is not helping, tools are breaking, just, you know. Sky-high analysis costs. Again, you know, there's costs for the tokenization to put in the AI, but also for me, you know, like my time is money. There are other tasks that I have to do. I can struggle. You've already seen that. Your tools can be used against you. Again, any defense mechanism, it can be turned around and used against you. And I say there's a customer disconnect, and basically for this is that sometimes customers complain like, hey, your sandbox didn't run this, do that, and you know, because what they're mainly trying to see is like the verdict, like good or bad, something like that. They don't just see the mountain of work behind the scenes that it has to go for. And I say there's cross-team engineering load. So the one for the VBS script is that it goes a customer person who calls in an engineer, who calls in a researcher, who then called in me, another researcher. I find the fixes. I go back to the head engineering, who pulls in 2 more researchers to implement the fixes, and then it goes to DevOps. So you have stuff that's like kind of simple, but it actually, there's quite a lot of load upon the whole engineering team. And I basically say thank you. I've got 3 seconds left. So, and so I would say probably no time for questions, but again, I'll be walking about getting water. So, dziękuję.